Awesome. So let's go ahead and get started now. It's pretty close to 7:05. So thank you guys again for coming out. This is Apply ML workshop number 5. Super excited for everyone to be here. And today we're going to be talking about a few topics. The first one is going to be KNN, and then second one is going to be different ways of evaluating your classification model. So let's go ahead and jump in. So, it's going to be the same format as usual. With our notebook, and we'll have the notebook up on our screen, and hopefully you guys can grab the notebook and follow along. So just go to that link right there, and that should take you to the notebook. Download it, and then open up Google Colab, and then upload your own copy. That way the work you're doing doesn't affect the notebook for anyone else here. And yep, Varun's going through the screen, the steps on the screen right now. So just go ahead and follow that, and you should be good to go. And yeah, we'll wait about a minute or two for people to get set up there. And if you have any issues accessing the notebook or uploading it to your Google Colab, let us know in the chat, and we'll try to work those out. The link is, let me put it in the chat. Oh, yep, Varun got it. Awesome. Oh. Awesome. Looks like Varun was able to get that running. If anyone hasn't got the notebook up on their end, can you please just drop a note in the chat, and we'll wait another minute or so. Going once, going twice. Okay, looks like we just had somebody new hop in. Hi, Sabrina. Thanks for jumping in. So to grab the notebook for today, go to this link right here, tinyurl.com/applyml5, and yep, just download that, upload that to Colab, and you should be good to go. Awesome. So we're gonna go ahead and get started. So as usual, we'll be going over a model today, and then if you guys remember during the first workshop, we talked a little bit about the machine learning pipeline, right? And the machine learning pipeline kind of goes like you start off with your raw data, you clean your data, you visualize your data, then you start working on the model itself. And then once the model is complete, you evaluate the model to see how the model's doing, maybe go back, tweak the model a little bit, make some changes, and then look at those evaluation metrics again. And then once you're satisfied with your model, you export your model to, whatever production or whatever use you have for the model. So in workshop 1, we went over that first stage, that like data cleaning, data mining part of it. In workshop 2, 3, and 4, we went over different models that you can use. Those were logistic regression, neural networks, decision trees, random forests. And today we'll be going over another model called KNN, which is short for k-nearest neighbors, as well as talking a little bit about that last end of the machine learning pipeline, which is evaluating your model. So that's what we have in store for today. As usual, we'll get started with simply importing our data. So just running these blocks of code for your, Varun, if you could just run these blocks of code, we should be good to go. So we start off importing the data just like usual. We split our data into the training and testing groups, just like usual as well. And yeah, then we check that, our X-train looks good, and yep, that's how it should be looking. Then of course, just like we did last time, verify that the train test split actually worked. And we do that, and yeah, looks like we are absolutely good to go. So yeah, just like I said earlier, today's workshop is going to be a little bit on the shorter side, just to give you guys a little bit of time to, take care of your midterms and anything else you have going on. So let me hand off to Varun now to talk a little bit about the k-nearest neighbors model.
Cool. So just to confirm, does everyone have the notebook up and running? In case you don't, drop a message in the chat. Going once, going twice. Okay, cool. So hopefully everyone's with us. So right, k-nearest neighbors is a very popular classification algorithm, and uh, what is the intuition behind such an algorithm, right? So one of the things is, let's say you're voting in the Democratic primaries or something like that. Let's say you haven't really researched about what the candidates' policies are and so on, and so you're not really sure who to vote for. So what do? You go out to the elections. You talk to 4 or 5 people out there. Of course, this was pre-COVID times when we wrote this workshop, so probably not the best idea to do that right now. But anyway, let's say you ask about 5 people, right? And 3 of them tell you they're voting for candidate A, and a couple of them say they're voting for candidate B. Since you don't really know whom to vote for, you just go ahead and decide, okay, 3 people are voting for candidate A, not as many are voting for candidate B. Let me go ahead with candidate A as well. So k-nearest neighbors essentially works in the same way. So if you graph all your training data based on their features, then if you want to classify a new example, what you do is you basically give it the class according to its nearest neighbors. So this is a visual representation of what we're trying to do, right? Let's say all the red and green points are your training data, and you have a new example point that you want to classify, right? The yellow question mark over here. And what you essentially see is that you look at maybe its 5 closest neighbors. So those would be these 3 red stars over here and the 2 green triangles over here. And you see that, okay, it's closer to the red stars than the green triangles. And so I'm going to classify this new point as class A. So this is a very intuitive algorithm. Basically, you assign unseen data to just the closest cluster that it's a part of. It's essentially just taking a vote. Or if you're closer to these bunch of points, then most likely the new data point also should follow the same class as your existing data, right? So like I mentioned, you're going to classify this yellow point as red because out of its 5 nearest neighbors, these 3 red stars and these 2 green triangles, it's going to classify into class A. Note that it depends on how many neighbors you choose. So instead, if I look at just 3 neighbors, like in this picture, just this red star and these 2 green triangles, then I would classify this new point into green because based on the 3 nearest neighbors, it would belong to class B. So of course, this whether you choose 5 neighbors, 3 neighbors, 7 neighbors, and so on, that depends on your problem, and the appropriate value will be determined on a case-to-case basis. So let's go ahead and take a look at this. So what do you think how do you think we would decide the best value of K? And do you think there are any bad values of K? Anyone want to take a stab at what a bad value of K would be? Right, so that's a good, we have some answers. I'm guessing we have n even numbers and 1. So all good responses. So if, for example, you chose your number of nearest neighbors as the entire, as the number of training samples that you have, right? That won't be particularly useful simply because, let's say your data set has 60% data points in class A and 40% in class B. Irrespective of whether your new data point is closer to one class or the other, since you're looking at all the data points, you're always going to say, okay, 60% of my nearest neighbors are in class A, So I'm just always going to end up classifying the new data point as class A, right? So it's obviously not useful to have an extremely large value of K, because in that case, I'm just going to be predicting the majority class every single time. And that's not particularly helpful for me. So one more response we have here is even numbers. And yeah, I guess that definitely makes sense in this case when you're classifying between 2 points, right? Basically because you might end up with a tie. But if you think about it, let's say we have a problem with where we're trying to classify a new data point into 3 different types of classes, then we would have to eliminate maybe all multiples of 3 as well to break ties. And so in general, you might have any number of classes. So you don't really care as much about whether K is even or odd or so on. Maybe a smart choice would be to, I guess, have K to be some kind of prime number. But in practice, if you have a tie, you can just break the tie based on which neighbors are closer. Or you can just arbitrarily decide that if 3 out of 6 neighbors are in one particular class, you can predict either A or B depending on what your preference is. And we have one last answer in the chat, that 1 is a bad choice for K. So 1 nearest neighbor is not the best idea. Does anyone want to guess why 1 is not a good choice? Feel free to think about it for a minute. Drop any thoughts that you have in the chat, or feel free to unmute yourself. Why would 1 be a bad choice for K? Right, so we have a couple of similar answers. So outliers, the argument being that outliers might exist, so K equal to 1 may not be super accurate. So that is definitely true, right? If your K is extremely small, you might just have a random data point close to you, but that might not be the right class, right? You might have maybe 50 other data points of the correct class near you, but you don't classify based on that simply because the closest one happens to be an outlier. So K equal to 1 may not be the most accurate. So what I want you guys to think about is, suppose you, like all the machine learning models we've studied before, suppose you split your data into a training and test set, right? Uh, is it possible for us to get 0 training error on our data? Do you think that's possible? Answers. If you think it's possible to get a training error, a 0 training error, try to tell us why. It, if not, try to tell us why you can't get a 0 training error. Once again, everyone can take a minute to think about it. So we have one response here that says that outliers might exist. So okay, so if the data set is small enough, isn't it technically possible? So so that's right. In a small data set, you might get 100% training accuracy. But the interesting thing about KNN is that you might have 100% training accuracy on any data set if you choose K is equal to 1. And that might seem a little counterintuitive, but what that basically means is that in the training stage, right, what is every data point's closest member? It's going to be itself. So it's kind of a stupid argument, but if you use K is equal to 1, then in the training stage, you're always going to have 100% accuracy, because every data point's closest neighbor is itself. And in the training stage, you would just assign its own class to it. So it's not really learning anything. So that's why K is equal to 1 is not a really good choice at all. And you would not expect such behavior to generalize well, because on the test set, you're most likely going to be able to classify a point correctly only if it coincides exactly with one of your training data points. So it's not the best idea to have K is equal to 1. So once again, this was a lot of information. So I'm going to stop for any questions. In the chat, just drop a 1 to 5. How comfortable are you guys with what the KNN algorithm is trying to do? Cool. So I'm seeing a bunch of 4s and 5s. If anyone at any stage has any questions, is not sure of something, feel free to stop me and we can go over it again. So one more thing I want everyone to think about is why do you think that one common phenomenon that we see is that there's almost always a gap between training and testing error, especially for KNN. And why do you think that is the case? Why would you always have a gap between training and testing error? It's kind of related to the case I mentioned before, where k is equal to 1. But yeah, feel free to take a stab at it. Why does KNN always tend to have a gap between training and testing error? Once again, you can take a minute to think about it. Feel free to take a guess, unmute yourselves, drop a message in the chat, whatever. It's related to the case when k is equal to 1. Cool. So I guess the main reason this happens is that even if you choose k is equal to 5 or k is equal to 6, right? Not just k is equal to 1, which is a relatively trivial case. Even then, in the training stage, for every data point, it's like its closest neighbor is itself, right? So you're always going to be biased towards the correct answer in the training stage simply because you yourself are your own nearest neighbor. So you can so in the training stage, it's guaranteed that at least one of your nearest neighbors belongs to the same class as you. So that tends to drive the training accuracy artificially a little higher. And that's why your testing accuracy tends to be a little lower, simply because in the testing stage, you can't reasonably expect that an unseen data point coincides exactly with one of the training data points that you already have. Right. So let's go ahead and see. We have one question in the chat here. So why would one of your closest neighbors not be yourself in the testing data set? Right, because when you're trying to predict on an unseen data point, you're only making use of the your training data, so you don't know the class of the new data point. So you classify that based on whatever's already there in your training set. One more question is, couldn't you ignore the nearest neighbor in the training stage? Yeah, technically you could do that as well. That's another approach to deal with the problem. Typically though, you'd want to include it because you'd want your model to have that information. Yeah, because let's say you happen to get a point that is exactly one of the training data points in the test set, even though it's unlikely to happen. You want to make use of the information that's already there. So you typically want the methodology you use in the training and the testing stage to be the same, except for what data you use. So it's just for consistency's sake, it makes sense to make use of that data point even during the training stage. But yeah, that's a good point. If you want to get a better estimate of what the true accuracy is, maybe you could remove the nearest neighbor in the training stage. Cool. So let's look at how exactly we can implement KNN using scikit-learn. Harsh, do you want to take over here?
Yeah, absolutely. Thanks for the handoff, Varun. So now we're going to implement KNN using scikit-learn. So just in this next block of code, we've left it blank because I think over the last 3 or 4 workshops, we've kind of drilled in that, there's a pattern with scikit-learn, and the syntax for training a model and getting predictions from a model is the same no matter what the model actually is. So if everyone could just take 2 minutes and initialize a vanilla KNN model and then fit it to the training data, and then also print out the training accuracy and the testing accuracy, that would be amazing. We feel like you guys will be able to do this because we've been doing some pretty similar stuff, in the previous workshops. So everybody take a minute or so to get that in. Awesome. So I think it's been about a minute or so. If anybody wants to drop into the chat what they've put in, that would be awesome.
So we do have one answer in the chat, and I think that's right. Yeah, so Brian here has given the code to do it in a single line, which is pretty much correct. If you wanted to, so let's just go ahead and run this. So you have a training accuracy of about 80%, and you have a testing accuracy of only about 68.5%. So that's expected to some extent because of the reason I mentioned before. If you want to make this clearer and write the code in 2 lines, what you could do is something like this. So you could essentially just initialize the model in one step and then fit it in the next step. This is exactly the same thing. Either way works, and you get the exact same results. Yeah, but what do you think about what value of k the model is using here? Anyone wants to take a guess?
I mean, since the training and testing accuracy are so different, and obviously they're not 0, or sorry, they're not 100. So it's probably like a low value, but not 1. So like 2 or 3 or something.
Yeah, that's a pretty good guess. Honestly, I do not know. If you go into the scikit-learn documentation, there's probably a default value that they have for this. But I'm pretty sure you're right that there must be some default value. So someone in the chat said it's 5. That very well might be the case. Yeah, in fact, I think it is 5. Someone else suggested square root n. I think square root n might be very large depending on how big your data set is. But occasionally you can decide what value of k you should start with by looking at maybe the dimensionality of the data instead. So if by n you meant the number of features, then maybe square root of n is a good place to start. Cool. So,
Awesome. So, oh, my bad, Varun.
yeah, continue.
Cool. Yeah. So, of course, Varun talked about extensively earlier how the performance of your KNN often depends on picking the correct value for n, right? And the way you change n in scikit-learn is with the n_neighbors parameter. So you can consider the n value to be a hyperparameter that is tuned to a specific data set. So in this case, we've simply changed n neighbors equal to 3. And Varun, if you go ahead and run that code, we can see what's happened here. So we can notice that, first we had, as Jin said, n neighbors of 5, and now we have n neighbors of 3. And we notice a very high train accuracy and a pretty low test accuracy, right? And what this screams to me is, and hopefully it screams this to you guys as well, is overfitting. Because whenever we have high train accuracy and low test accuracy, usually the case is overfitting, right? So are the terms K and N used interchangeably? No, I should have said K. My bad. Was I saying N? My bad. My bad if I was saying N. It should be K. Sorry about that, guys. Good catch. Good catch. Thanks for that. Okay. So yeah. Even with different Ks, with a K of 3 and a K of 5, we notice that there's overfitting happening here, right? So we don't really have a ton of data here. I believe if we go back and look at our data set, we have about like 800 or so data points. Yeah, about, right? So that's really not a lot of data for a KNN to learn from, especially given the large number of features we have. So usually when you have a large number of features but a small amount of data, a KNN will overfit. And the reason for this is a concept called the cursive dimensionality. So Varun, if you could just run that really quick, and it should show a small graph. All right. So as you can see, what this graph essentially is showing is that there's a happy medium between the number of features you have and the performance of your model for a specific size of a data set, right? And the more features you end up adding to your data set, if you keep the amount of data the same, the performance of the classifier is going to go down because there's too many different features and not enough data for it to identify which features are the best features to use, or for it to identify which features are properly correlated with the answer. So the neural network, or in this case the KNN, is not going to have enough data to identify what exactly the optimal values should be. So that's essentially what the cursive dimensionality is. So, a lot of times in ML, you get told that, adding new features will only help. But, for KNN specifically, that's not the case, because you'll get hit with this concept known as the cursive dimensionality. So that was a kind of a lot of information in the last 30 seconds. So can you guys drop a 1 through 5 in the chat of how you guys feel about the cursive dimensionality? And, if I need to explain anything else regarding that. Threes and fours. Okay. Yeah, I think just the big takeaway from the cursive dimensionality is that, as you increase the number of features in your model, your classifier performance will likely drop if you don't exponentially increase the amount of data as well. So, we're noticing this overfitting here. So let's try and reduce the number of features that we're giving our model and see if that helps with our performance. So let's just drop a few of the features. So in this case, we've dropped fair, port Q, port S, things like that. And we should have our new data. Yep. And then, of course, as usual, we need to do our training testing split, which should be next. Yep, there it is. And then finally, let's try our KNN once more. So, okay, so we're doing a little bit better now, right? We noticed that the test accuracy did go up a little bit as compared to before, but there's still a pretty sizable gap of 7% between the train accuracy and the test accuracy. So just in my mind, the next thing that I would think of is like, okay, if this is all we can do with the data, let's try changing something in our model. And I think the most obvious thing to change here is, the value of K. So let's try different numbers of neighbors and see which one gets us the best performance. Thankfully, our data set is pretty small, which means that KNN can run pretty quickly, which means that, we can try a whole range of different values, right? So in our case, we're trying every odd number, from 1 through 99 inclusive. So, if we just scroll through here, we can see that there's some values that are really helping us get, good testing accuracy and similar testing accuracy, as to our train accuracy. I believe, when I was looking at this before, I think the best value was 13, which is on the screen here. You have pretty much identical training and test accuracy with about an 80% split for both. And then, as you continue to increase K, the training and test accuracy only drops. And I think you should see that as Varun scrolls down, right? We started off with about 80% at the top, and now we're all the way down to, 66, 65%. So yeah, seems like in this case that K equals 13 is our best value to go with about an 80% training accuracy and an 80% testing accuracy. So that's probably the best we can do on this model, right? 80% isn't amazing. We've found that we've had better performance with different models in the past, but it seems like this is likely the best that we can do for this specific model. And yeah, Vern, if you could maybe just clear that output and then go on to the next bit here. Awesome. So let me hand back off to Varun to talk a little bit about why people use KNNs and what the advantages of those KNNs are.
Cool. So Harsh here just went through how you can basically vary the number of nearest neighbors and then look at what the best performance is. In practice, does anyone want to take a stab at how you would choose the optimal value of K? So know that a train test split might not always be enough. So what's the best way of deciding whether K should be 13, 5, 20, or whatever, right? As usual, drop a message in the chat or unmute yourselves, whatever works.
Hint, this is related to something we've done in a previous workshop.
Right, so Kyle here suggests that we should try cross-validation, and that's exactly right. Cross-validation is usually the best way to determine hyperparameters for our model. So like we discussed in previous workshops, what you would do is instead of just a train test split, you would have a training, cross-validation, and a testing split. You would basically predict on the cross-validation data with different values of K. And then whichever K value does best, that's what you pick and use to predict on the testing data. So we haven't implemented that code over here, but that might be a fun exercise for you, for everyone to try out after this workshop is done. So maybe if you use a cross-validation data set and then determine the optimal value of K, take a look at what kind of performance you get. And yeah, try to maximize your test set accuracy. In addition to this, right, Harsh did mention that we got better classification accuracy on some of the previous classification models that we used, like a neural net, for example. That being said, there are a couple of major reasons why KNN is still practical and useful in a bunch of different use cases. So does anyone want to think about why is KNN useful? What is the major advantage of KNN? There are a couple of them that are kind of related. And one of the clear advantages is that it's easily interpretable. So a neural network might be seen as a black box. With logistic regression, you have a bunch of weights that you need to train, you need to use gradient descent and so on. It might be a little complicated, right? So, but KNN is intuitively very easy to understand. You simply classify a new data point based on the closest data points in the training set. So it's intuitive. So that's one advantage, right? Anyone can easily understand what KNN is about. But in addition, there are two other advantages of KNN. So I'll wait a minute for any guesses to come in. Why is KNN useful? Take a minute to think about it, and then we can go ahead and discuss. Even if you're completely off base, just say whatever you're thinking about. Right. Yeah, I mean, it is simple. And Christine here says that you can add more data points easily. That's actually exactly right. That is one of the major points, is that KNN is what you call an online algorithm. And what this means is that let's say you get a new data point in your set, right? In your training data. And this could very well be possible. So for example, if you're watching a bunch of shows on Netflix and you decide you've already seen 100 shows, and based on that, Netflix can use maybe nearest neighbors on your unseen shows and predict you what you should watch next. Now, let's say you watch that 101st show, right? It's very easy for Netflix to once again run k nearest neighbors on these 101 data points instead of just the original 100 data points without any major change to the algorithm. It's online in the sense that you can add new data points quite easily. So this is a big advantage because it doesn't mean, so if you start off with 100 data points and someone gives you 5 more at a later stage in your training data, you don't have to retrain the model at all. You can basically make use of these new data points almost instantaneously. So can add more data points easily. So that's one major advantage. And I guess the first advantage is related to this. It's that training is essentially free. Because note that you don't really need to train anything. You just have a training data set. And when you predict on any other data, it's you then have to just look at your training data set and see which neighbors are the closest and classify based on that. There's no gradient descent, there's no modifying the weights, nothing of that sort. Training, you essentially don't have to do anything in the training stage, right? So that can save you a lot of computation. But that being said, you always have a trade-off in machine learning. So because training is essentially free, when you're predicting, that's when you might have a problem. Because in KNN, when you're trying to predict on a new data point, to find the k nearest neighbors, you have to look at all the data points in your data set. And note that that's not something you would do in, let's say, a neural network, right? Or logistic regression. Once you've got your optimal set of weights, you don't even care about the training data anymore. But in KNN, although you don't have to spend any time actually training your model, when you're actually predicting, you have to loop through the entire data set to find the k nearest neighbors, and that can be an expensive process. So while training is relatively cheap, prediction can often be quite expensive. Prediction can be expensive, right? So if you, for some reason, have a lot of time to make your prediction, but you don't want to keep retraining your model and you want to make use of new data, in that case, KNN might be the appropriate algorithm to use.
Awesome.
Right.
Varun, thanks for that explanation. So I also wanted to check in with a concept that we had talked about a little bit earlier, and then try to tie it back into our KNN model here. So we noticed at best our KNN model got an accuracy about 80 on the train set and about 80 on the test set, right? So would anyone have any ideas just based on something we talked about in an earlier workshop, I believe workshop 3, on how we could improve the performance of this model? And I think one thing I want you guys to keep in mind is that KNN uses distances between points in order to make its predictions. Any ideas? Feel free to, drop an idea in the chat, or to, come off mute and say it out loud. Okay, so what I was referring to was data scaling. So if you guys remember in the third neural network workshop, one thing we did to the data during our pre-processing stage was that we scaled the data so that every feature had a mean of 0 and a standard deviation of 1, I believe, is what we did. So oftentimes doing something like this will really help the performance of a KNN, because a KNN simply uses distances between different points in order to calculate, what the prediction for the current point will be. So if we have, for example, one feature that is, measuring in centimeters, and one feature that is measuring in miles, the value for centimeters will be a lot higher, because a centimeter is a lot smaller of a unit than a mile is, right? So in that case, the KNN is going to weight that feature a lot more heavily, because the centimeter will contribute a lot more to that, the distance between points, because its value will be so much higher than the mile. So I want everybody to take about 2 minutes right now and rerun the chunk of code we had where we tried to find the optimal value for k. But before rerunning that, I want everybody to scale the data that they put in to the data they put in to that part of the model, and scale it so that it has a mean of 0 and a standard deviation of 1. So this should be pretty easy if you reference one of our previous workshops that talked about the standard scaler. And yeah, I'll give everybody about a minute or a minute and a half to try and get that in. So yeah, I'm not sure if you guys have used the Jupyter Notebook before, but if you want to add in a chunk of code where you can put in this new, scalar, you can just go like right above, and hit the plus code button. And yeah, Varun, if you do that, and yep, and you can use the arrows on the right side to move code blocks up and down. So you probably want to scale your data before you run the model. So that's how you create the code block, and you can just move that right up before the training and prediction itself. And yeah, so right there in that new block you just created, just try to put in the standard scaler and try to scale down your data. It's just xtrain.var axis equals 0. I don't think so. I see what you're trying to do there, but try using the standard scalar package. sklearn will like take care of all of that for you. You won't have to assign it by specific variable itself. All right, so it looks like it's been about a minute and 30 seconds. So if anybody has any ideas on how to do that, put it in the chat. If not, Varun can just go ahead and put in the answer. All right, looks like there's nothing in the chat. Varun, if you want to just go ahead and code that out for us. So yeah, pretty standard, similar to how we did it, or actually exactly the same to how we did in workshop 3. We're first going to import the standard scalar, then create a scalar object, scalar equals standard scalar. Then similar to how we fit machine learning models, we also want to fit the scalar to our training data. So that's x_train. And then of course, you also want to scale the testing data as well using what you learned from the training data. So yeah, so Varun, if you could just get the testing line in there, x_test equals scalar.transform x test, perfect. So yeah, now if we run that chunk, that will scale our data. And then if we go ahead and run the chunk of code above to see if our value, our optimal value for k has changed, hopefully we'll see some increased performance. It's also possible that we don't though. Okay, just to keep in mind, previously our accuracies were 80 and 80. So just looking at our numbers here, we are seeing much improved performance. Even if you just look at the nearest neighbors of 3, we see 86% train accuracy and about 82% test accuracy, right? And then yeah, just scrolling down, looks like our accuracy, for 25 is really good as well, because 23 and 25 is really good as well, because the training and testing accuracy numbers are quite close. And as you decrease, it seems like the performance gets worse, and then it kind of stabilizes towards the end where it stays around 79%. So if you guys noticed a big change, I think you guys can notice a big change that happened in the model performance simply by scaling, right? Before, the best performance we were getting was about 80 and 80. And now the worst performance we're getting is about 79 and 79, right? So there's been a tremendous difference in the performance simply from scaling. So I think it's important to remember that with KNN, scaling is super important, because KNN is based on distances between points, and we want the model to treat different features and analyze features equally, and don't scale all the data down so it has the same mean and same standard deviation. It's very possible that it will naturally just gravitate towards one feature to the other, and that's not what we want it to do. Okay, looks like we have a quick question in the chat. So the reason why scaling increases our accuracy is because the model puts less weight on the distances between data points. So I think that's one way to think about it. I think the way I think about it is so if you look at like two different like features, right? So let's say like you have some feature that's like small, like in very small units, and then you have one feature that's in really large units, right? The way k-nearest neighbors works is that it'll calculate the Pythagorean distance between, or no, Euclidean distance, excuse me, between two different points, right? And the way it'll do that is the simple like, x minus x1 minus x0 squared plus y1 minus y0 squared square rooted. So in that case, if there's one feature that has a really small unit and then one feature that has a really large unit, it's possible that, because of the way we calculate Euclidean distance, one of those features is going to be weighted much more greatly than another feature. So in that case, that one feature will have a lot more say as to what happens than another feature would, and that's not what we want to happen. So I guess a good way of saying it is that the model puts like less weight on one feature versus another, but I think you don't want to say that a model puts less weight on the distance between data points, because the only thing k-nearest neighbors actually looks at is the distance between data points. So that was kind of a long answer, but hopefully that makes sense.
So before, distance wouldn't have been heavily biased towards age. It seems that age has the largest variance. Yeah, so it's very possible that it could have been heavily biased towards age. My guess though is that I think the feature with the biggest like raw values was price, because I think like the ticket prices ranged from like 0 to like 60 or 70 if I remember correctly. So I think I would guess that price is the feature that it was most heavily biased towards. So, okay, that was a lot of information from, about the scaling and the distances regarding KNN. Can everybody drop like a 1 through 5 in chat about how they feel about the use of scaling in KNN and why it's important? Seen 5s and 4s. Awesome. And seen a 3 from Jacob. Okay. So does anybody have any questions, or does anybody want me to, go over anything again? Because the scaling thing is a really important thing when it comes to KNN. So want to make sure everybody understands it.
So the reason why you'd want to scale is by first looking at the data set, right? That's how you gauge which columns or like features might be like skewed to one direction.
Right. So if you look at our scalar, that's actually exactly what we're doing, because scalar.fit_xtrain looks at our entire training data set, and then the scalar learns like, what it needs to do to different features in order for them to have the same mean and the same variance. So once the scalar learns that, it then simply transforms the xtrain and transforms the x-test, if that makes sense.
And scalar.fit does the scaling for all the columns in our data set, right? Not just the, like, can you specify a column if you want to only scale, for example, price?
I'm sure that you can. I'm not super familiar with it. But usually like in ML models, it's like pretty standard to scale your data no matter what model you put into, and you usually like scale every single feature. So I'm sure there's a way to do that using sklearn, but I'm not familiar with it.
Got it. Thank you.
Yep. And Jacob says, I don't know if this makes sense, but is it kind of like z-score? Man, my AP stats knowledge is kind of out
Yeah,
the
I think it's
window
the
right now.
yeah,
It's been a while.
Z-score.
Oh yeah, z-score is okay, I just googled it. The number of standard deviations from the mean value. Right. Yeah. So you're right. That's actually exactly what you're doing. You want to standardize that across the data set as well. All right. Any more questions? Going once, going twice. How does scaling work with categorical features? Can KNN work generally with categorical features? So great question, Kyle. So if you remember in one of our previous workshops, we mentioned that machine learning models don't handle categorical features. Not okay. So with categorical features, usually what we do is you will like put in like a 0, 1, 2, 3, or 4, and then like depending on how you value it, you will either one hot encode those values, or you'll just assign a single like numerical digit to a to different categories, right? So in that case, there's usually not a correlation between what the value of that category is to the category itself. So in that case, a KNN would probably not be your best choice for like for a data set that is very heavily categorical, because the KNN will just simply look at the numbers and interpret it as if like the KNN is not going to change anything about how it runs, because it's just going to look at distance again. No matter whether it's a numerical, like actual numerical value, or a categorical feature. So in that case, I would say like a KNN is probably not the best choice of model, but yeah, I mean the model will work because it's just numbers, and of course the KNN will be able to calculate a distance, but it's just likely not your best choice. Sorry, that was kind of a scrambled answer, Kyle. Did that make sense? Okay. Not seeing anything from Kyle, so hopefully that made sense. Yeah. What was the other thing you were going to touch on at first? Yeah. Initially, I thought when you said categorical, you meant like non-numeric, but what you actually meant was like discrete variables, not like a continuous variable. So I just interpret your question correctly. Awesome. Any more questions?
Cool. So let's go ahead. So we've kind of completed all the models that we wanted to talk about. Talked about logistic regression, we talked about neural networks, talked about decision trees, talked about random forest, and today we finished up KNN. So that's like 5 models in your tool belt that you can use to, attack any ML problem that comes at you, right? But of course, once you've created your ML model, you need a way to evaluate it as well. So far, we've been using accuracy. And, in a lot of cases, accuracy sounds like the natural choice, right? A lot of things in life are measured off accuracy. Your grade, if you're an athlete, like your free throw percentage in basketball is accuracy, right? But oftentimes accuracy isn't the best choice in a machine learning model, right? So let's just take a look at a few case studies that are detailed in the notebook to talk about maybe why accuracy isn't always the best choice. So, in that second paragraph, let's say we talk about like a lottery ticket, right? So let's say we design an algorithm that can given a lottery ticket number, tell you whether or not that lottery ticket number was a winning ticket, right? So let's say that, instead of doing any fancy machine learning, we simply just wrote an algorithm that told you that every time it saw a lottery ticket, would just simply tell you, no, this lottery ticket is not a winner, right? That algorithm would have an accuracy of like 99.9999%, right? Because lottery winners are really, really rare. I think like the number is I think you have like less than 100,000th chance of winning a lottery or something like that. So even if the algorithm guessed no every time, it'd have a very, very high accuracy, right? But again, this algorithm is completely useless. It does not provide any actual value because it doesn't actually do anything, right? It just simply guesses no. So even though that this is a really, really bad model, it still has a very high accuracy, right? So I think the point of that was just to illustrate that oftentimes accuracy can be really, really misleading. Another example is, detailed in the first paragraph. So let's say we were trying to design an algorithm that identified whether or not something coming into Polypavilion, is a hazard, right? Well, most of the time, things coming into Polypavilion are not hazards. Usually it's like a water bottle, it's somebody's phone, it's somebody's wallet, right? Typically people are not bringing like knives or bombs or like things that are dangerous into Polypavilion, right? So if this model was trained on a data set that accurately represented the distribution of objects coming into Poly, it again would be accurate 99% of the time because the vast majority of objects coming into Poly aren't hazardous. So once again, accuracy is useless here because the model can just guess no every time and still be accurate 99% of the time, and that's not what we want from our model, right? So we kind of need to take a step back here and think about different ways of evaluating the performance of our model that are beyond accuracy. So I'm going to hand off to Varun now to talk a little bit about what a confusion matrix is, and that should be a good intro into better ways to evaluate our model.
Sorry.
Varun, I think you're on mute. Yeah, there you
go. Right. So if you want to measure the performance of such algorithms in such use cases, right? You don't necessarily care about the accuracy, like Harsh mentioned, but you do want to make sure that when you actually do have a winning lottery ticket, or when you actually do encounter someone who might be carrying a dangerous weapon, your model identifies them correctly. So it's very natural to measure of the following terms when you're evaluating a machine learning model. So the first thing is true positive. So when the actual result is positive, how often does your model give a positive result? So this would basically translate to when you actually have a winning lottery ticket, how often is your model able to correctly identify that? So, and similarly, when you actually have someone who's dangerous, can your machine learning model effectively catch them when that person is dangerous, right? So now note that this is obviously a much better way to measure the performance of your model when you have data that is heavily biased, right? 99% of the times you want to classify no, but it's only in that 1% of situations where you really want your model to work well. And so that's why true positives are important. Uh, then you also have the false positive rate uh, when the expected result is negative, uh, but your model still predicts positive, right? Now this could be a case where you have TSA. They basically search a bunch of people even though they're completely innocent, uh, just to be on the safer side for whatever reason. And you want to minimize the false positive rate, right? You don't want to catch people who are not actually carrying dangerous weapons, or you don't want to buy a lot of unnecessary lottery tickets, ideally, if you want to crack the system, right? So you want to increase your rate of true positives and you want to reduce your rate of false positives. And true negatives, when the result and the expected result are both negative, you want to maximize this particular situation, right? When someone is not actually dangerous, you want to make sure that your model predicts they're not actually dangerous. And yeah, so I mean, these models will naturally have a relatively high true negative rate, um, because they're biased, but that might not necessarily be the case all the time. And naturally, you also have false negative, where uh, the expected result is negative, um, but you don't. So when the expected result is positive, but you predict negative, so that's probably the most dangerous situation. Yeah, I there's a small error here. So false negative is when the result is negative, but the expected result is positive. This gets confusing if you don't spend a lot of time thinking about it, because there's a bunch of false negatives and false positives and so on. So a false negative is probably the most dangerous, uh, because this essentially translates to there is someone who is pretty dangerous, but your model says that no, they're completely fine. They don't actually have a knife or a bomb with them. So this is what you definitely want to avoid in a lot of places. So yeah, that was a pretty good catch. So using all these definitions, we can create something called a confusion matrix. So before going on to that, are there any questions about any of these definitions? Some of you may have come across this before. Um, let's look at the chat. Uh, Result is positive, expected result is negative.
So yeah, that's a false positive, right? So false positive is like when your model predicts a positive, but the actual value in real life is negative. Like, if my model predicts that this is a winning lottery ticket, but it's actually not a winning lottery ticket, that's a false positive. Okay. What are you confused about? Is it just like all four definitions in general, or? Cool. Let me run through the definitions one more time, just using the okay. On the thing it says false positive, actual result is positive, expected is negative. Yep, it does say that. Right. So I think exactly. Jin's got it exactly right. So the result in this case is the result of the model. It's what the model is predicting, right? So like in the case of a false negative, that's when the model predicts that we don't have a winning lottery ticket, but we actually do. So the expected result is reality. Correct. The expected result is reality. Sorry, we should have made that more clear in the write-up here. Yeah, no, you're totally chilling. This is like super easy to confuse. So, because they're all just exact opposites of each other. So yeah, so great addition by Kyle there. So result is what our model is outputting, and then the expected result is like the true value in real life. So yeah, can everybody just drop like a 1 through 5 in the chat about how they're feeling about these 4 definitions? Because these are pretty important to what we're about to talk about soon. Seeing 5s. Awesome. That's great to see. Cool. Great. Sorry for interrupting you there, Varun.
Oh yeah, you can go ahead and explain.
Yeah, for sure. So Varun, if you just hit play on that, that code block. Awesome. So this is a confusion matrix, right? This shows you exactly like what the values for your certain data set are, right? So it'll show like actually positive and then actually negative versus predicted positive and then predicted negative. And then it'll calculate a fraction of, true positives, false negatives, and true negatives. So when we're referring to a confusion matrix, we're essentially just talking about this right here. And the confusion matrix is pretty integral to talking about other ways of evaluating our classification model. So let's make our own confusion matrix, and Varun, if you could just scroll down. So here's our practice data, and awesome. So we have a predicted column and we have an expected column. So we want everybody just to take 2 minutes and try to make your own confusion matrix. You don't have to print it out in like a super pretty format or anything. Just try to get the values of, the true positives, true negatives, false positives, and false negatives for this data set. So yeah, give you guys about 2 minutes to do that, just to make sure, this concept is rock solid in your guys' minds. Awesome. Has anybody been able to, calculate the 4 values? If you could just drop them in the chat, that'd be awesome. Cool. No worries. We'll show you guys how we did it. So we kind of cheated a little bit, and it turns out sklearn kind of has everything for anything you want to do, and that includes creating a confusion matrix. So we're just going to go ahead and say from sklearn.metrics import confusion matrix, and then we're going to print out the confusion matrix of the data expected versus the data predicted. And yep, Varun's just putting that in there. Data predicted.
That seems to be taking a little longer than expected. Or what?
Okay, wait. I think Varun's back. Varun, you there? Varun, I think you're on mute.
Sorry, my
There
internet
we go.
cut off there for a second.
Yeah, no worries. You're totally fine. So yeah, if you just want to screen share, and we'll get back to it.
Oh, cool.
Awesome. So it looks like we're back. And yeah, you can see that, sklearn has printed out our confusion matrix. And this is, pretty much exactly what we're looking for. So it will have the true positives, false positives, true negatives, and false negatives. So in this case, since we're doing binary classification, true negatives is, C of 0, 0, which is 11. And then, C of 1, 0 is false negatives. And then in the bottom right, we have true positives, which is 15, C of 1 and 1. And then false positives is C of 0 and 1, which is 13. So yeah, this is, that's exactly what this is. And so we just wanted to, is this including the trained data and test data or just the test data? So this is like not like trained data or test data. This is just like, in order to create this like quote unquote data, we actually just generated random numbers from 0 through 1 for predicted, and then generated random numbers from 0 through 1 for expected, and then just tossed it into a data set, because we just wanted to use this to just to show the concept of, creating a confusion matrix, and then, the concepts of, true positive, false positive, all that good stuff. So yeah, this isn't anything like with a training or a testing set. Awesome. So now that we're able to do that, let's talk about precision and recall specifically, right? So let's see like exactly what the definitions of those definitions are. So Varun, if you could just run that code block for us. Awesome. So recall equals true positives divided by true positives plus false negatives. And precision, on the other hand, is equal to, Varun, if you could scroll, it'll show us what that is. Yep, true positives divided by true positives plus false positives. So these are two specific metrics. Before we talk about what exactly they are and where they're useful, see if you guys can, using the data from above, calculate what the precision is and what the recall is, for this data set that we have. So if everybody could just take like a minute or so to try to get that in. And hint, there's definitely a scikit-learn function out there that can, do what you want to do. So see if you can find that and try to work that into your code here. So yeah, I'll give you guys about a minute for that.
So just for convenience, what you guys could do is basically just store the confusion matrix in a variable, and then you can access individual values like this. So that might make it easier for you all to work things through. Alternately, of course, you guys could use precision score that's inbuilt in sklearn metrics, like we used the confusion matrix function. There should be a similar one for precision and recall as well.
Yep, I think we've hit about a minute. So Varun, if you want to go ahead and put in the answers. So very, very similar to what we just did. So, from sklearn.metrics, import precision score. And then of course, we don't want just precision, we want the recall as well. So we'll say sklearn.metrics import recall score as well. So yeah, as Varun's getting that in there. And we want the recall score as well. So and then, right. So then now we can just go ahead and say, precision score of y true, comma y pred. So in our case, the y true and y pred will be the expected and the predicted. So once again, it'll be like the exact same code that we used for getting the precision matrix, except, or excuse me, the confusion matrix, except this time we'll have our prediction, our precision score as well as our recall score rather than the confusion matrix. So yeah, recall score and prediction score, or excuse me, precision score. Vern, you want the precision score, not the prediction score.
Oh yeah, my bad.
Yeah, you're totally fine. And then if we run that, that should tell us, what our score is. Okay, cool. So we're getting like 60%, 53%. So, that's pretty expected. As we said earlier, we made this simply by, getting we just generated like two random arrays and called one of them predicted and one of them expected. So this is pretty expected. And, that's how it'll usually be with random numbers. So now let's talk a little bit about when we want to use recall and when we want to use precision, right? So recall is something that we want to use when we want to minimize the number of true negatives, right? So recall would be good to use in a situation like security, right? Because we want to make sure that we don't let anything into polypavilion that could potentially be hazardous. That means that if we throw out a few things that are good uh, on accident because we're being super strict about what we're letting in, that's totally okay. So with a recall, we're kind of erring on the side of caution of what exactly we let into polypavilion. We're erring on the side of caution of saying what exactly is okay. We're erring on the side of caution when we make a prediction for something, that is a true negative. So what was the second print statement? Yeah, Vernon, if you just want to scroll up real quick and show that. But yeah, so recall is important when we're doing something like security here, right? Because it's much better to check a few extra items than to accidentally let in an item that is hazardous. So now let's talk a little bit about precision. Vernon, if you want to scroll down to our precision section. So precision is a good choice when we want to maximize true positives. This means that when we predict something is a positive, we want to be absolutely right that that it is a positive. So one example where high precision could be important is the criminal justice system, because when we're convicting someone, we want to be 100% sure that that person is guilty, right? It's a pretty famous saying in America, right? Innocent until proven guilty. So until we have no more doubt that that person is innocent, we don't convict them, right? In my opinion, it's better to let a few guilty people walk free than to imprison innocent people, right? So precision would be important here because we want to be absolutely sure that when we convict someone that they are actually deserving of that crime and we're not imprisoning anyone that's innocent. So does that make sense? Precision and recall, the scenarios in which we'd use one or the other. How does that sound to you guys? Do you guys want to drop a quick 1 through 5 in the chat of your understanding of that? Seen a 5, seen another 5, seen some 5s. Awesome. That is great to see. Cool. So let's talk a little bit about F1 score now, right? Because oftentimes we're humans are greedy, right? We don't want just one or the other. We want both. So in this case, and in most situations, we usually want a balance of precision and recall because we don't want to be making too many mistakes on one side or we're making too many mistakes on the other side. We kind of want a balance, right? So a good way to get balance is using an F1 score, right? And F1 scores are important because we don't want like too much recall. Like for example, we could easily get 100% recall by simply marking every item going into polypavilion as a hazard, right? That means we would, let no hazards in, but obviously that's not what we want, because that means we'd let nothing in at all, right? So we can use an F1 score in this situation. So Varun, if you want to run that code block, it'll show what an F1 score is. So the formula for F1 score is pretty straightforward. It's simply the weighted average of both, which you can rewrite as 2 times precision times recall divided by precision plus recall, right? So it's simply the harmonic mean of precision and recall. So let's use the next cell to find the F1 score of our precision of our practice data. So if everybody could just drop in a code block and then maybe take a minute to find the F1 score of our practice data that we have here. So yeah, I'll give you guys about a minute for that. Syntax should be super similar to what we've been doing previously for confusion matrix and precision and recall. So this one should be pretty straightforward. Oscar says from sklearn.metrics import F1 score, print F1 score data expected, data predicted. Oscar hit the nail right on the head. That's perfect. Varun, if you want to put that in to our code, that's exactly what we're looking for. So yeah, I mean, I think you guys can definitely see the benefit of the sklearn library here, because everything is standardized. Even with the model training, it was always .fit, and then .predict, right? And then in our case here, with the F1 scores and the confusion matrix, precision recall, it's all very, very similar to each other in terms of syntax and in terms of use. So yeah, F1 score here, we see about 56%. Once again, that's pretty expected just because we were using completely randomized data. So yeah, so those are just a few different ways to evaluate models. There's a few more advanced ones like area under the curve, ROC curves, things like that, which are often used in machine learning as well. But we wanted to leave those two as an exercise to you guys. If you guys are super interested in trying to explore other tools and other ways of evaluating your model, I'd recommend starting search with AUC and ROC curves, and expanding from there. Those are two of the most popular ones used in ML today. So can you somehow weight precision, recall, and F1 score? Yes, Cameron, that is a fantastic question. You actually can. There is a way to do that. I believe there's a scikit-learn function for it that'll do it automatically for you. I'm forgetting the name of the name of the metric, but there is a way to do that. So, Cameron's right. In some situations, you want a little more precision or a little more recall. There's a way that you can tune your F1 score just to get that in. What would be a good interpretation of the F1 score in the context of the polypavilion example? So I think in the case of the polypavilion example, it's tough because F1 score is probably, in that case, we probably want a weighted F1 score that's probably a little more biased towards recall, just because we don't want hazards to get in. But I would say like F1 score is like you're trying to find the happy medium between like not letting any hazards in, but also not stopping too many people at the gate. I think that one's a little tough to do an example for, just because letting a hazard in would be catastrophic. So sorry about that, but I think that's the best I can do on that one. But yeah, that is the end of our workshop today. Does anybody have any more questions? Feel free to drop it in the chat or come off mute.
I had a quick question about the confusion matrix from above.
Yep, shoot.
So I just wanted to clarify what it contains. So those are all the counts of each of the like true positive, true negative, false positive, and false negative in the data set, right?
Right.
Okay.
Yeah. So those are the count. That's not like your percentage or anything.
Got it.
Right.
And the way it uses that is simply by looking at like 1, 1, 1, 0, and then if it's like 1, 1, it knows it's a true positive. If it's like 0, 1, then it's a what, like a false negative.
0, 1, false negative. Yep, exactly. That's actually exactly what it does.
Cool. Thanks.
Yeah, for sure. So yeah, with that, we've reached the end of our ML pipeline. We've talked about the start of the pipeline, data cleaning, data processing, the middle of the pipeline, models, and then finally the end of the pipeline, which is evaluation. So this is actually all of the specific teaching workshop content that we have for you guys. So this is actually the end of the road as far as it comes to teaching for us. So thank you guys so much for coming out. Like we said, this was our first time, running this workshop. So we're super excited. We were super excited to get this out to you guys, and hopefully it's been helpful for you guys as an intro to ML and as an intro to scikit-learn and the machine learning process in general. So we are planning, however, to have a few more workshops. We won't have one next week because our workshop directly coincides with the AI research panel. So everybody should go out to that instead of our workshop. But we are planning to have a few more workshops that are going to be project-based, where we give you guys a project and we have you implement some of the things and use some of the skills that we've taught you in this workshop to try and get through that project. So more information about that will be coming soon. We're not 100% sure yet whether we'll be doing that live, everybody together during like this usual time, 7 to 9, or if we'll just do it asynchronously and have some check-ins. We'll keep you updated regarding that. So that should be in about 2 weeks from now. And yeah, that's all for us. That's everything from us for today. If you guys have a chance, please fill out our feedback form if you can. Like I said, it's first time running that workshop, so every little bit of feedback helps to make our workshop better for next time and next year. And Varun, if you have anything else, I'll let you say something.
Harsh, I think the feedback link is broken.
Oh boy.
Yeah. Sorry, everyone. Just stick around for a minute so we can fix the link and send it to you.
Oh, my bad. Looks like it is broken. Let me fix that. Yeah, give me a second. Just going into the drive right now to get that. Okay, cool. I'm actually just going to directly put it into the chat for everyone. Yeah, if you could, it's that second link there, that short one. If you could just go there and drop us some feedback, that'd be fantastic. Yeah, Varun, if you have anything else.
No, I guess that's about it. I hope everyone learned something from the workshops that we had, and we hope to see everyone implement some machine learning models and do some interesting stuff.
Yeah, thank you so much for coming out, guys. I think that's all from us. We're going to sign off. Feel free to stick around and ask us any questions. We'll hang out for a minute or two, but if not, thanks so much, guys, for coming out, and we'll see you at the future projects workshops, whatever those may entail. Yeah, thank you guys for coming out. You guys made the workshop. Yep, see you, Jacob. And yeah, Vern, if you want to stop the recording, looks like we're good to go.
That worked?